SANDHAN, All Gujarat Integrated Classroom.
સેટેલાઇટના માધ્યમથી જોડતી કડી એટલે સંધાન.
Good afternoon, students. Welcome to the track of mathematics, and today I will be talking to you about interpolation. First and foremost, let us find out what is interpolation. Interpolation is finding the value of y corresponding to a given value x. For example, let us consider two variables x and y, where x is an independent variable and y is a dependent variable. Let y be a function of x, that is y equal to fx. Let it be a function which takes values y1, y2, y3, so on to yn for the values x1, x2, x3, so on to xn respectively. That is, for a given independent variable x, takes on the values x1, x2, and correspondingly y, which is a function of fx, that is y is dependent on x, takes on the values y1, y2 respectively. Given such an equation, say x is the independent variable and y is the dependent variable, which is given by the formula f of x, or we can say that y is a dependent function of x. So when x takes on the values x1, y becomes y1. When x is x2, y equals y2. When x is x3, y equals y3. And so on, when x equals xn, y equals yn. So given a table for independent variables x1, x2, x3, we have dependent variables y1, y2, y3 corresponding to the value of the function at the given independent variable values. Now, if this f of x is known explicitly, then for any value of x that lies between x1 and xn, that is within the set bound, that is if we have got n values for x beginning from x1 to xn, and if fx, that is the function, is known to us, the form is known to us, say ax squared plus bx plus c, or any other form of fx is known to us, and if the value of x lies between these bound values x1 and xn, then the corresponding value of y can be computed. And if fx is not known explicitly, we do not know what form of the function is, then we need to find a simple function phi x such that it approximately agrees with the function fx. Now, we do not know the form of fx, but we approximately find a function that fits into phi of x. Then this process of fitting a simple function to the set of values is called interpolation. So the process of finding or approximating a function phi of x such that it almost agrees with the unknown fx is called interpolation. Let us now understand this graphically. We have got the values of x at the x-axis, x1, x2, x3, x4, and the y-axis represents the value of the function at any given point x1 to xn. That is, y equal to f of x is represented on the y-axis. Let us say we have got n set of points, say x1, y1, that is at x equal to x1, y is equal to y1, x2, y2, x3, y3, so on and so forth, n points, xn, yn. Now, when we plot these points and try to draw the function f of x, this is how it would look. So, if we know f of x explicitly, the blue line denotes the function. But since we do not know f of x explicitly, we now need to fit a function curve such that it approximately agrees with f of x, which we have denoted here with a red dotted line, dashed line. Now this dashed line actually represents phi of x, which closely represents f of x, not totally but closely represents f of x. Then this process of approximately finding phi of x, that approximately agrees with f of x is called interpolation. It is not f of x, but it approximately fits into f of x, and that is why we call this process interpolation. Now, this is interpolation. Why interpolation? Because the point in question for which we would be approximating this curve, or we would be approximating this function phi of x, would lie between the bounds x1 to xn. That is, given the tabulated points x1, x2, x3 and xn, the point x in question will always lie within the set of points, and that is why we say inter, that is between the intervals x1 to xn, and that is why we call this process interpolation. So if the approximating function phi of x is a polynomial, then the process is defined as polynomial interpolation, and henceforth in this particular session we would be talking about polynomial interpolation. But before we actually go on to learning polynomial interpolation, there are certain terms or terminologies that we need to understand. First of them is finite differences. Now, what are finite differences? They refer to differences between the value of the function or the differences between the past differences. So, any difference. Now, when I talk about differences between the value of the function, what does it mean? Given the points x1, y1, x2, y2, x3, y3 and xn, yn, our yi's represent the value of the function at xi's. Now, when we find the difference between the yi's, that is between the value of the function, then that is called the difference between the value of the function. Now, when you find out these differences and further compute the differences between the past differences, then it is called the differences between the past differences. So in either case, these are finite differences. Differences can be categorized into 4 categories: forward differences, backward differences, divided differences, and central differences. Let us first have a look at forward differences. And within forward differences, we shall first talk about first order forward differences. Let us assume we have the values x1 to xn given to us for the independent variable x and the corresponding values y1 to yn for the dependent variable y, where y is represented as a value of f of x. Now, given this particular table, we know that x1, x2, x3 and xn are the independent values, or are the values of the independent variable x, whereas y1, y2, y3, yn are the values of the function f of x when x takes upon the values x1, x2, x3, xn respectively. In this case, the difference of the value of the functions, that is y2 minus y1, y3 minus y2, the corresponding differences, y3 minus y2, y4 minus y3, so on and so forth, yn minus yn minus 1. These are the differences, or I would say the corresponding differences between 2 consecutive values of the function. So these differences are termed as forward differences, and the difference is denoted by delta. So we use a triangle which is representing delta. Therefore, we can say delta y1 is equal to y2 minus y1, delta y2 is equal to y3 minus y2, delta y3 is equal to y4 minus y3, delta yn minus 1 is equal to yn minus 1. Now we'll wonder that we had already n points. Then why delta yn minus 1? Since this is a difference of corresponding differences, the last difference would be 1 degree less than the total number of points that we take. So if we have got n points, the last degree for the first order would be 4n minus 1. So if there are 4 points, it would be 4 minus 1, which would be 3. So it would be delta y3 rather than delta y4. So these are the first order differences. Let us now understand this through a table in a tabular form. We have got x and y, where x1 corresponds to y1, x2, y2, x3, y3 and x4, y4 are already the points that are given to us. We need to compute the first order forward difference that is denoted by delta y. So delta y1 is equal to y2 minus y1. Difference of the value of two corresponding functions, or rather I would say two corresponding values of the function. Similarly, delta y2 is given by y3 minus y2 and delta y3 is given by y4 minus y3. I hope this is understandable now. Very simple. Now, why don't we have delta y4? Because there are 4 points and y4, the value of the function at x equal to x4, has already been utilized in computing the first order forward difference delta y3. So all the values of the functions have been taken into account and hence we do not go further. So if we have got n points, the last value that we would compute would be delta yn minus 1. Now let us have a look at the second order forward difference. Second order forward differences are the differences of the previous order forward differences. That is, we just computed delta y1, delta y2, delta y3. So delta y2 minus delta y1, delta y3 minus delta y2, delta y4 minus delta y3, and delta yn minus 1 minus delta yn minus 2 are termed as second order forward difference. Second order because they are differences of the first order forward differences. And these differences are denoted by delta square or delta raised to 2. So delta 2y1 is equal to delta y2 minus delta y1. Delta 2y2 is equal to delta y3 minus delta y2. Delta 2y3 is equal to delta y4 minus delta y3. So on and so forth. Delta 2yn minus 2 is equal to delta yn minus 1 minus delta yn minus 2. Now, why do we have delta 2yn minus 2 for a set of 4 endpoints? The reason is first order differences could be computed up to yn minus 1 and the second order differences would be again 1 less than the previous and hence it is yn minus 2. So if we have a set of 4 points, then the second order differences can be computed up to y2, that is delta 2y2. Why? Because it is n minus 2, 4 minus 2, which is equal to 2. Let us have a look at the tabular form. The values of x and y are given to us. We take the same example as we did earlier. And a little while ago, we computed the first order forward difference delta y, which is already known to us at this juncture. Now we need to compute the second order forward difference. And as I mentioned earlier, the second order forward differences are the differences of the previous, that is the first order forward differences. So delta 2y1 is given by delta y2 minus delta y1. So it is the difference corresponding to the values of the first order forward differences. Similarly, delta 2y2 can be computed as delta y3 minus delta y2. Now, since there are just 4 points, we can compute up to n minus 2 and n minus 2, that is up to 4 minus 2, that is 2, and hence you can see on the screen that we have computed the second order forward differences up to delta 2y2. Let's go further to compute the third order forward differences. Again, the third order forward differences are the differences of the previous differences. So the difference between the values of the second order forward differences will help us compute the third order forward difference. So delta 2y2 minus delta 2y1, delta 2y3 minus delta 2y2, delta 2y4 minus delta 2y3, and delta 2yn minus 2 minus delta 2yn minus 1 are called the third order forward differences, and they are denoted by delta cube or delta 3. Therefore, delta 3y1 is equal to delta 2y2 minus delta 2y1. You see, it is the difference of the previous or the second order forward differences. Delta 3y2 is equal to delta 2y3 minus delta 2y2. Delta 3y3 is equal to delta 2y4 minus delta 2y3. So on, delta 3yn minus 3 is equal to delta 2yn minus 2 minus delta 2yn minus 3. The third order forward differences can be computed up to n minus 3. That is, for a table of 4 points, it would be up to 4 minus 3, that is 1. So for a table of 4 points, there would just be one value of the third order forward differences. Let's have a look at it in the tabular form for a better understanding. So again, we have the same table, x and y. x1, y1, x2, y2, x3, y3, and x4, y4 are the 4 points that are known to us. We had earlier computed the first order forward differences as delta y1, delta y2, and delta y3. We also computed a little while ago the second order forward differences, delta 2y2, delta 2y1, delta 2y2. Now we shall compute the third order forward difference. The third order forward difference at y1 can be computed as the difference of the second order forward difference, which can be given by delta 2y2 minus delta 2y1. Now all the values of the second order or the past forward differences have been taken into computation. As a result, we cannot go further. So there is only one value in this particular table for the third order forward difference. And if you remember the formulation, that is, we can go up to n minus 3. So for this table of 4 points, we can go up to n minus 3. That is 4 minus 3, which is 1. And that is what we have already computed.